When you first learn to program in CUDA, you are told that thread blocks cannot communicate with each other. Today we will explore a clever and fundamental communication pattern to communicate between thread blocks. Using the global memory as a shared scratchpad for thread blocks and some atomics and spin locks, we can come up with a pretty powerful programming paradigm. Let's recap a little bit. This is the input array. Our goal is to perform an inclusive prefix sum operation to get to this output array. Now, if we break this work up in parallel thread blocks and just have each block scan its local section, we end up here. This is almost right, but we need to add the total sum of the preceding block to every element in the current block. This creates the need for communication between thread blocks, which are normally independent. And this is the central challenge. Now, one way to solve this communication problem is with a hierarchical scan. This uses multiple kernel launches to get the job done. Each kernel has to finish, write its result to global memory, and only then the next kernel can start. We already covered this method in detail in a previous video, so I'll link that in the description if you want a full recap. The goal of this video is to do everything in a single kernel launch. Coming back to the problem, when we launch the kernel, all the thread blocks are working at the same time. To get to the correct final scan, block 0 somehow needs to communicate its sum to block 1, and then block 1 needs to communicate the total sum to block 2. But thread blocks can't synchronize with each other easily. So how do we make them pass these messages safely? We can use something known as a message passing pattern. To do this, we'll set aside a buffer in global memory to act as a shared scratchpad that all blocks can access. After block 0 finishes its local scan, it writes its total sum to this buffer. Then after block 1 finishes its local scan, it can just go and read what block 0 wrote. But wait a minute, what happens if block 1 finishes its local scan before block 0 and attempts to read from the buffer? That's not good. We read from the buffer before block 0 got a chance to write to it, and as a result we corrupted all the data in block 1 by adding garbage to it. To protect against this, we will keep a separate buffer of flags. The idea is every block can write its result and then signal the flag to let other blocks know that its value is now safe to read. This time around, after block 1 finishes its local scan, it will first check if block 0 has set the flag. The flag is not set, that means block 1 will not read from the results buffer. After block 0 finishes its local scan and writes out its result, it will signal the flag. At this point, block 1 can read from the results and add to its own values. Continuing this further, after block 2 finishes its local scan and tries to read from its slot, it finds that block 1 hasn't written to it yet. After block 1 writes and signals the flag, block 2 can safely read. This creates a chain of communication, block by block, all within one kernel. That's why it's also sometimes known as a chain scan. Here's what this communication pattern looks like in code. Once block 1 finishes its local scan, we elect the first thread to be the block's communicator. It then waits for block 0's flag. This while loop just spins until the flag is 1. Now from block 0's point of view, as block 1 is continuously spinning and polling in a while loop, block 0 might still be running its local scan. Once its local scan is done, it elects the first thread in the block. This thread finds that the flag is already set to 1, so it can safely read from the results. Obviously, the result is 0, so adding it to its value will not change the result. Finally, block 0 writes out its result and signals the flag. Block 1 can now safely read the result and update its values. Then it becomes the producer. Finally, it sets the flag by atomically adding 1. Block 2 starts by locally scanning its subarray. After that's done, it checks if block 1 has already signaled the flag, which it did, so block 2 can safely read the result. And we're done. These lines of code are called memory fences, and they serve a very important role. Because CUDA has what is known as a weakly ordered memory model, the compiler or the GPU are free to reorder memory operations like these. For instance, if we remove the memory fences that prevent the load reordering, the compiler might reorder these loads and we will load result before the flag is signaled. Similarly, if we were to remove the fence which prevents store reordering, the compiler might output something like this, which is again wrong because we don't want to signal the flag before we actually store the result for the next block. So now that our memory ordering is correct, there's still one bug in this code. It is this line. This whole chain assumes that block 0 runs, then block 1, then block 2 in perfect order, based on their block index.x. But a GPU is massively parallel. The scheduler can launch blocks in any order. So what if a block with a higher index is scheduled before a block with a lower index? For instance, what if block 5 is scheduled but block 4 hasn't even started yet? Block 5 will just spin in that while loop waiting for a flag from block 4. But block 4 can't run because all the GPU's processing units might be tied up by other spinning blocks. This is a classic deadlock. The fix is to stop relying on the physical block ID, block index.x, to determine the order. Instead, we use a global atomic counter. When a block starts, the first thing it does is atomically increment this counter. The value it gets back is its dynamic block ID. So the first block to get scheduled, no matter what its block index.x value is, will get ID 0. The next block gets ID 1 and so on. Now our spin lock logic is based on this dynamic ID. The block with ID 1 always waits for the block with ID 0. We are guaranteed that the block with ID 0 is actually running because it's the block that successfully claimed that ID. This breaks the deadlock. With all that now, we have a functional implementation of the single pass scan. Let's see how it performs. It is nearly 7 times slower than the hierarchical approach. Well, that was disappointing. In one of the future videos, we will see the reasons behind the horrible performance and see what we can do to improve it.